We shall now discuss steel stadiums. Stadiums are large, purpose built facilities designed to host sporting events, concerts, and other form of entertainments that require a sizable audience capacity. They typically feature a central arena or a field surrounded by tiers of seating, along with amenities such as concessions, restroom, and sometimes VIP suites. We can have sports stadiums which are designed for sporting events such as baseball, football, rugby, cricket, etc. Or we can have multi-purpose stadiums that are built to accommodate various types of events beyond sports, including concerts, conventions, trade shows, community gatherings, etc. We will restrict ourselves to steel stadiums, although stadiums can be built in precast concrete and concrete structures. Also, a steel stadium structure refers to the framework or skeleton of a stadium that is primarily constructed using steel component. Steel is often chosen for stadium construction due to its strength, durability, and versatility. Beside this, we can have speed of construction and safety attributes related to steel stadiums. The stadiums can also be considered as a single space steel structures. Thus, the variables responsible for distinguishing one form from another are applicable in case of stadiums. We discussed in our earlier lectures that one structural form can be distinguished from another structural form by keeping the functional framing, stability system, construction technique, and foundation systems different. The main philosophy of load transfer within a stadium structures is similar to the single space structures. We are familiar with the load transfer in these two different types of single space structures. The structure system on the left hand side is consisting of series of portal frames which are connected via purlins or horizontal members. The gravity load from the external sheeting will be transferred to the purlins and then from there onwards distributed among the portal frames. And from the portal frame, it will come down to the ground. The lateral load, if applied in the plane of the portal frames, will be easily transferred via the fixed connections of the portal frame down to the ground. Thus, if the lateral load is in the transverse direction, then that will be distributed among the portal frames and then the portal frame will bring it down to the ground. If the lateral load is in the longitudinal direction, then we need another truss system to transfer the load down to the ground. So we provide a truss system in the roof called as wind girder and the elevation bracing. This system bring the longitudinal lateral load down to the ground. Essentially, the bay which is braced is the stiffest bay and hence attracts most of the longitudinal lateral load. On the right hand side, we have another system where again frames are stacked one behind the other, but this time these frames involve beams and column structures connected with each other via simple connections. Therefore, all these frames are unstable in plane direction. The gravity load in this second system will be transferred similar to the first system. The lateral load in the longitudinal direction again will be transferred in a similar way as the portal frame system. So we see that for the lateral load in the longitudinal direction, we have a truss system transferring that load down to the ground. However, there is another truss system provided in the transverse direction to transfer the lateral load in the transverse direction down to the ground. The reason this transverse truss system is provided is because that all these frames are unstable in plane direction. Hence, in order to stabilize them in plane direction, a longitudinal wind girder and elevation bracing are provided. These elevation bracing are at the gable ends of the system. The frames which are at the ends are called gable ends. So the same type of systems can be exploited in the case of stadium structures. We will now discuss a very well-known football stadium called as Ashton Gate Stadium in Bristol, United Kingdom. This is a stadium made up of lattice structures. In this view of the stadium, we can see a big lattice girder on the top, and there are some cantilevers sticking out. This lattice girder is supported by these gable frames which are at the end. So we have a lattice girder shown over here and some cantilevers being supported by the lattice girder. This is another view of the roof showing a braced roof, a lattice girder, and these are the cantilever beams being supported by the lattice girder. In this view, we can see the same lattice girder supporting these cantilevers. The cantilevers are hidden under the sheeting. Similarly, there is a series of cantilevers going all around the stadium. These cantilevers are tied with each other in order to have an integrated structure. In this drawing, we can see the same lattice girder being supported by the framing at the gable end, and the lattice girder is actually supporting cantilevers underneath. This lattice girder is almost 100-meter long. The plan of the roof is shown over here. We can see that the roof has got X bracing for lateral stability. We can also call this as a wind girder. So this is similar to what we had in the single space truss system. An X wind girder was provided in the roof. In the case of Ashton Gate Stadium, we have two big X bracing stabilizing the whole roof. In this drawing, we have the lattice girder supporting the cantilever beam as shown. So in the 3D image, there is a series of these cantilever beams stacked behind each other, and these are all supported by this lattice girder. The roof plan clearly shows that the whole roof is divided into vertical and horizontal grid lines. The gable frames are located at grid line 5 and grid line 20. These are two frames supporting the lattice girder. This is the elevation at grid line 14 and 15. So according to the roof plan, 14 and 15 grid lines are in the middle. This elevation clearly shows that the lattice girder is supporting the steel cantilever. The steel cantilever has got a back propping steel system responsible for transferring the load back to the ground. Beside the roof structure, there is a permanent steel structure that supports seating and provides accommodation for offices and public amenities. On the ground level, we have a concourse or meeting area, toilets, changing rooms, etc. We can see that on the first level, we have a restaurant. The second level has got hospitality room, lounges, etc. Similar amenities are provided on level 3. We also have a permanent structure which supports the seating arrangement. All these structures are made up of steel and have got bracing provided for in-plane stability. This is the elevation frame at grid line 5, which is the gable end. We can see that there is a support system provided to transfer the reaction of the lattice girder to the ground. The construction of the Ashton Gate Stadium is as follows. In the first stage, the rear stand is erected. After that, the lattice truss is built in the front of rear stand. After that, the cantilevers are installed. These cantilevers are hinged at the back. We can see that the orientation of this cantilever in the roof is initially parallel to the seating arrangement. Finally, the lattice girder is placed on top of the cantilever and the roof is hinged up. Some of the picture from the construction site are shown over here. So we have the grandstand already built and the lattice girder being assembled. The lattice girder is being assembled and is almost complete, whereas the cantilevers are installed. In this picture, the roof cantilevers are being installed by the crane. This is the 3D model of the stadium. We will now discuss another stadium called Brentford Community Stadium. This is also a football stadium shown over here. This stadium has got steel cantilever trusses stacked one behind another all around the stadium. The cantilever trusses are joined with each other by straight members. There is also a steel truss connecting all the cantilevers around the stadiums. This picture shows the cantilever trusses which are placed all around the stadium. And as we saw in the picture previously, that there is a straight member joining all the cantilevers together. And also at almost the mid length, there is a steel truss joining all the cantilevers. In the case of Brentford Community Stadium, the load transfer is similar to the single space steel building. We have the gravity load being transferred via the cantilever frames. The lateral load, on the other hand, can be transferred via the series of wind girder system and the elevation trusses. As we can see, the whole system is braced in order to have a fully integrated structural system. This is the typical elevation of the Brentford community system. Again, we have a permanent structure supporting seating arrangement and also a grandstand. There is a back propping system supporting the cantilever. This is one of the other elevation. Thus, we can see that steel stadium structures are used worldwide in construction of different sports venues. From the framework of supporting the seating bowl to the roof trusses spanning over the playing field, steel plays a crucial role in the construction of modern stadiums.